Today's lecture is going to be very brief. We didn't talk about determinants in class on Wednesday, and I'll do that on Friday. I just want to say a few things about section 1.7, some practical considerations about the computational aspects of matrix operations. So a basic kind of question that you ask is of the following. Here's a simple one. Suppose I have A is an n by n matrix, and V is an n vector, or an n by 1 matrix, and I want to compute A times V. If I want to know how long that's going to take, the basic measurement the question is how many basic operations does this require? Operations does this take? And by basic, I mean either multiplying two numbers, adding two numbers, or multiplying two numbers. Well, this is quite easy to estimate. You have an n by n matrix, so that's A11, A1n, AN1 up to ANN. And you're multiplying this times B1 down to Bn. And how many operations does it take, for example, to compute the first entry in the result? Well, you have to take the dot product of this row with this column in order to get the first entry in the answer. And how many operations does that take? Well, there are n multiplications and n minus 1 additions. So these are multiplications and these are additions. So why is that? So you have to multiply A11 times B1, that's one multiplication, and the second one times the second, and so on, up to A1n times Bnn. So that's the n multiplications. And after the first one, every time you do one, you need to add it to the previous one. And so there are n minus 1 additions. So this is 2n minus 1 operations. And so in order to get the entire result, you're going to need to compute n of these, C1 through Cn. So you're going to have to do this n times. So the answer is n times 2n minus 1. And what you really care about is neither the 2 nor the 1 so much. The main point is what's the power of n. The highest power of n which occurs is n squared. And whenever you're talking about estimates of computations, the first thing, the most basic question is, what's the power of n? And the higher the power of n, the worse it is. And this isn't too bad. N squared is the power. So that says, for example, if n is equal to 100, then this number that you're getting is on the order of 10,000. And I don't really care that this number is really, I'll write it out, it's really 2n squared minus n, because if it's 10,000 or 20,000 or 9,950, the order of magnitude is what counts. So this is n squared. All right, well, let's bump this up just a little bit. What if I asked you to multiply 2n by n matrices? How many operations does that take? A times B. The number of operations is approximately, well, to get the first column, you needed approximately n squared, and you need to do that for each column, so I'll just write that as n squared times n, which is approximately n cubed. Okay, so you just think of the matrix B as being B1 through Bn. Each of these is a column vector, and this takes n squared, this takes n squared, that takes n squared, and n times n squared is approximately n cubed. So that's a basic fundamental estimate that multiplying matrices is on the order of n cubed. And n cubed is getting to be a bit of a problem. For example, if you want to multiply two 100 by 100 matrices, then what is n cubed? Well, that's 10 to the 6th. And it's growing pretty fast as n gets bigger. Okay, let's look next at Gaussian elimination. Suppose I have an n by n matrix A, and I want to reduce it to upper triangular form. Well, there's a little bit of an analysis in the book. I'll just summarize it rather briefly. So when you're doing Gaussian elimination, at some point you get to the, let's say we're at the jth row from the bottom. So you have j rows left. And you've already taken care of this stuff and this stuff. And what's left is you have to deal with this j by j square. And so it starts off as working from the top. You have an n by n square to look at, and then n minus 1 by n minus 1, and so on. And if you count the operations, it turns out to be roughly 1 squared plus 2 squared plus 3 squared plus ... n squared. And there's a simple algebraic computation that you can see to see that this is approximately n cubed. So well, that was just extremely terse. If you want more details, see the book on page 50. But the moral of the story is that Gaussian elimination takes approximately n cubed, and that's pretty much the same thing as saying computing the LU decomposition. The cost is approximately n cubed. So that's all I have to say about those estimates, and I'm not going to talk about tridiagonal matrices. I just want to say a few things about pivoting strategies, and I'll just illustrate this with an example as in the book. Suppose you had the augmented matrix 0.01, 1.6, and 32.1, and 1.622. And suppose that you were doing the row and column operations to solve this equation, the system that this came from, and well, you have this 0.01, and 0.01 is not 0. Mathematically, it's really not 0. Computationally, it's kind of close to 0, but anyway. So if you were to do the obvious thing here, you would, in order to kill that 1, you would multiply the first row by minus 100 and add it to the second row. And when you do that, you get 0.01, 1.6, 32.1, and here you get your 0, and here you get minus 159.4, and the last entry is 22. Oh no, sorry, minus 3188. Minus 3188. Okay, well, that's not terrible, but those are fairly big numbers, and when you work this out to get the answer, what you get is the following. Well, here's the scary thing. Suppose that I'm lazy, and instead of using 3188, I just rounded it off to 390. That doesn't seem like a big deal. That's convenient. It makes the calculation a little easier. And if you do that, what you get is that y turns out to be 3190 over 159. Oh, and I'm also gonna round this off to 1 minus 159 and round this off to 32. And what I get is y is approximately 20.1. And when you go back and you plug in for x, what you find out is that x turns out to be approximately minus 10. And you put this on your paper and you hand it into the professor, and the professor marks it with a big X and says that no, the correct answer is y is equal to 20 and x is equal to 10. So the y was close, obviously, but the x was terrible. It came out minus 10 instead of 10. And the problem is the size of these numbers. With this, when you plug this calculation in, this little 0.1 here winds up multiplying by something and giving you an enormous error. And so this is a warning sign that when you're doing matrix calculations, small errors can mushroom quite fast. And so you need to be extremely careful when doing estimates. Now, what you would do in this example is the following. Well, rather than worrying about these silly round-off errors, there's a much simpler way to proceed, which is to simply switch the two rows and get yourself a better pivot. The problem here was this 0.01 required you in order to multiply this row by minus 100. And that blows things up and causes all sorts of trouble. So instead, just switch the two rows to get 1.622 and 0.01 1.6 32.1. Now when you do the obvious thing, in order to make this work out, you're going to multiply the first row by minus 0.01 and add it to the second row, and that's going to give you 1.622. Zero, 1.594, and 31.88. Okay, and so now let's do our little round off. Let's call this 1.59. Let's cross that out. And let's call this 31.9. And then if you proceed, what you conclude is that y turns out to be approximately 20.1 as before, and x turns out to be approximately 9.9. And that's quite respectable. If you can check, I mentioned this on the previous slide, the actual solution is 20 and 10 for y and x. So the moral of the story is that mathematically it makes no difference which way you go, but in terms of the effect of rounding, it makes a huge difference. And this is called a pivoting strategy. So the smart way to pivot is to is to always permute your rows so that the largest number is your pivot. So the basic pivoting strategy in order to take care of this is you apply a permutation matrix, permute the rows at each step so that the pivot is the largest possible in absolute value. So that is to say, if you have a column and you're looking at 1.1.01.3 and 2, if these are your choices for pivots, you choose the biggest one and you move that up to the top and you use that as your pivot.